This is 4.1, and we're talking about the parabola. And we're going to talk about the parabola in a different way. We're not going to talk about the parabola in ax squared plus bx plus c standard format. That's not really how we're going to talk about it. To get to where we want to go, let's take a trip back in time. So let's say that it's 1200, you're in Greece in a toga, and you have a big box of sand, and you have a stick, right? So you take the stick and you make a point in the sand. You're consumed by this idea of equal distance. And so what you'd like to know is, if I gave you another point, like this point out here, there's a distance between these two. Where are all the other points that are the same distance from the blue dot as the red dot are? So you could say, well, if this is D, there's probably a red dot over here that's also a distance D. And there's probably one over here that would be a distance D. And another one over here, and one here, and one here, and here, and here, and here. And if you started to fill in all the dots that are equal distant from the blue dot, what shape would you get? You'd get a circle, right? That's sort of the definition of a circle, is all of the dots that are the same distance from a center dot. And we're going to define a circle in a different way in a little bit, but for right now, this is good enough. No Cartesian coordinate system, okay? No x and y axis. Rene Descartes has not even been born yet. So all you're doing is you are in like a sandbox and you're drawing things in the sand. Okay, get it? But you're consumed by this idea of equal distance. Well, let's take another example. Let's take this blue dot again and let's add another blue dot. So let's put another blue dot down here. So we'll call this D1, dot number 1, and this is D2, dot number 2. And maybe what you want to know is, where are all the points that are equal distant between these 2 points? So now it's not just one single point, but it's where are all the points that are the same distance between these two. And so right away you could say, well, gee, if I connect these with a line, and I found the midpoint of that line, we'll call this D, and we'll call this D. Those are the same distance, right? Well, where are the other points that are the same distance? This distance would be the same as this distance. And if you went here, this distance would be the same as that distance. And if you went here, and here, and here, and here, same distance from there to there. So if you plotted all these points, what shape would you get? You'd get a line. And this line has a specific characteristic. We would call it perpendicular. Every point on it is the same distance from the top blue dot as it is from the bottom blue dot. So that's lines. So we kind of talked about circles. We talked about lines. Let's change it once again. Let's leave the same blue dot, and this time let's make a line. Where are all the points that are equal distant between that point and now a line? So again, right away, you're kind of like, oh, gee, if I do that perpendicular trick again, like this, I could cut that in half, and this would be 1 point right there. This line has to be, we'll call this L2. It has to be perpendicular to L1. So when I draw this line, it has to go like this, and this line has to go like this, and this line has to go like this. They all have to be perpendicular. So if this is a distance, there's a distance, and those lengths are the same. And these 2 lengths are the same. And these 2 lengths are the same. So here's a dot A, and there's a dot D on the line, and there's a point E in between them. And you can see I've measured the length from A to E and from E to D. And you can see it's the same length, 3.63. So what happens if I move D? Can you see how E moves? And if I move it like this, 8.63, 8.63. Equal distant between a point and a line, with the condition that the segment ED has to be perpendicular to the line, right? It's got to be perpendicular. And if I swing it this way, zoop, 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 what shape does that make? I'm going to turn on, I'm going to select point E, and I'm going to turn on trace, and watch this. What shape is that? It's a parabola! And so this is the definition of a parabola. Parabolas were not originally defined as ax squared plus bx plus c, complete the square, blah, 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 quadratic formula. Parabolas were originally defined as all the points that are the same distance between a point and a line. That's how parabolas were born. That's how people came up with the idea of a parabola. Pretty cool, huh? All right, so with this parabola, we know a couple points. This point right here, we would call the vertex. Now that we've invented the parabola, we've come up with this definition where the parabola is the set of all points that are equal distance between a line and another point. Now let's let René Descartes be born, okay? So now Descartes is born. The vertex has coordinates h, comma, k. Remember our friends h and k from complete the square format? Okay, so now we have an xy axis, and the vertex is located at the ordered pair h and k. We also have to bring forward this original definition that we had like 1,000 years ago, right? We got to bring together the line and the point that created the parabola. And so the point, this point here, is called the focal point, and the line down here is called the directrix. So what we have here is we have bringing forward the information that we had defining the parabola. We have a focal point and the directrix. And the parabola itself are all of the points that are equal distant between the focal point and the directrix. So we have the focal point. We have the directrix. Those are the two important players. And the result of the equal distance thing is you get this blue parabola. Now there's another characteristic that we want to identify, and that's the distance between the focal point and the vertex. This is called p. That means the distance from the vertex to the directrix is negative p. Here's the equation. X minus h squared equals 4p y minus k. This takes into account the vertex, h and k. So like here's your vertex, right? Here's h and k. And those values go here and here to this h and this k. The distance from the focal point to the vertex is called p, and that value goes right there. X and y are your generic variables, so we're just going to leave them x and y. And this is the equation of this parabola. But notice this equation doesn't reference like ax squared plus bx plus c. This is an equation written in a format that only considers the vertex and the point P. So all you need to know are h and k, where the vertex is, and the distance from the vertex to the focal point. And you can come up with this equation. So let's look at an example. Find the following characteristics for this parabola. What is h? What is k? And what is p? So what's h? Negative 7. What is k? Negative 1. And what is p? Yeah, p is equal to 3. You know that, like if you look at the yellow region, you know that 4p has to equal 12. So now we know h, we know k, and we know p. So let's make a sketch. So this is our vertex. We're going to call that negative 7, negative 1. And this is a point on the parabola. This is the vertex of the parabola. We also know p. P is equal to 3. So you go up 3 units. That's the location of your focal point. You go down 3 units, and that's the location of the directrix. So let's see. Let's answer some questions. So what is p equal to? 3. Where are the coordinates of the vertex? Negative 7, negative 1. What are the coordinates of the focus, or the focal point? Well, I know it's got to be a negative 7, right, because it's the same x coordinate. But yeah, you're going to add 3 to that y coordinate. So this is going to become a 2. So I'm going to say negative 7, 2. What is the equation of the directrix? And again, you're looking at this negative 1 here, and you've got to go down 3 units. So how about y equals negative 4? And then axis of symmetry, oh, we know what that is, right? That's this line right here that goes down the middle of the parabola. So that's an old friend. We know that. X equals -7. Find the equation of a parabola that has a focus at 5,11 and a vertex at 5,5. The first piece of information we're given is that our focus is at 5,11. So that's a focal point. They also tell us the vertex, and that's at 5,5. What is P? P is equal to 6. You subtract the y coordinates, so 11 minus 5 is 6. If you go 6 units up to get to the focal point, you need to go 6 units down to get to the directrix. And what's the equation of the directrix? Y equals -1. Look at that. We've got a focal point, we've got a vertex, we've got a directrix. You could probably kind of pencil in maybe what the parabola is going to look like, something like this. So could we come up with an equation? X minus h squared equals 4p y minus k. Do we know h and k? Yep. Do we know p? Yep. Let's plug them in. They want it in y equals. So that means we've got to solve this thing for y. It means we need to get y, this guy right here, all by itself. That's the equation of this parabola in standard format. X squared plus 40x equals 4y minus 32. And remember, our structure is we would really like to get this in x minus h squared equals 4p times y minus k. That's the format we'd really like to get this into. Over on the right side, this 4y minus 32, that looks like it's going to be pretty easy to do. You just factor 4 out of everything. But what about this guy? What about going from here to here? But what we're looking for is a technique that will take that x squared plus 40x and convert it into a perfect square. We're going to run complete the square on that. So you're going to take x squared plus 40x plus blank minus blank equals 4y minus 32. Just when you thought you were done completing the square. Great. So what goes in the blank? b divided by 2 squared, which is 400. Good. So we're going to add 400 and we're going to subtract 400. And now, believe it or not, this guy right here becomes x plus 20 squared equals 4y minus 32 plus 400. So I'm going to take this minus 400 here. I'm going to add it to both sides. Let's finish this up. What is p equal to? 1. What is h equal to? What's k equal to? Could you sketch this? Our vertex, and that has coordinates -20, -92. From there, you go 1 unit up, and that is your focal point, not drawn to scale. And you go 1 unit down, and that is your directrix. Could you figure out what those coordinates are? Sure, mathematically, you could say, oh, well, I've got a -92. I need to add 1 to that. So the coordinates for the focal point are going to be -20, -91, and the equation for the directrix will be y equals -93, because you go 1 unit down. 1 unit up to the focal point, 1 unit down to the directrix. Variations. There's 2 things we want to talk about. The first one is your p-value. If p is positive, a positive value, then that means that you go from the vertex up to the focal point. So you would go something like this. So here's the vertex, and this would be your focal point. And parabola's always open. This is p being positive. Parabola's always open towards the focal point. Or in other words, the focal point is always inside the parabola. What if p was negative? If p is negative, then that means your focal point is below the vertex. That's a negative p, and the parabola would open down. The second thing involves, we're going to call this which variable is squared. So in our standard equation, this guy, x was the squared variable. So if you have x minus h squared, then your parabola opens up or down. There is another version of this equation that looks like this. Y minus k squared equals 4p x minus h. And in this case, y minus k is what is squared. So do you see the difference between these two formats? One has the x minus h being squared, the other one has the y minus k being squared. But you still got an h and a k, you still got a p. This parabola opens left, right. It's a sideways opening parabola. So the blue parabola is going to look like this, or it's going to look like this. The green parabola with the y being squared will either open to the right or open to the left. So if it opens to the right, this is a positive p, and it opens to the left, this is a negative p. Just like with the blue one, if it opens up, you've got a positive p, and if it opens down, you have a negative p. Is this one going to open up down, or is it going to open left right? The x is what's squared, so it's going to be an up down opening. So it's either going to open up or it's going to open down based on what p is. What is p? P is 5, and so this is going to open up, right? Oh, this is boring. Do you have another one? Okay, cool. Where is your vertex? It's going to be 1, 9. H and k are still with x and y, right? So that doesn't change. So your x coordinate's going to be a 1, your y coordinate's going to be a 9. What is p? P equals 8. And how'd you get 8 so fast? 32 divided by 4. You know that this guy here has to equal 4p. So if it's a 32, you just divide it by 4, and that'll tell you what p is equal to. Finally, does this open up, down, or left, right? It opens left, right. So if p is positive 8, I start at my vertex, 1, 9. Which way do I move to get to the focal point? To the right. So I'm going to move 8 units. 1, 2, 3, 4, 5, 6, 7, 8 right here. This is my focal point. So this is my focal point, and could you find the coordinates of that focal point? Yeah, I know the vertex is 1, 9, so I add 8 to the x coordinate, and that gets me 9, 9. If I go 8 units the other way, this is the location of the directrix. And this directrix goes up and down. And it's going to have the equation x equals -7, because you're going to go -8 units, and then you're going to go +8 units. That gets you to the focal point, and then the directrix. And this parabola is going to open up towards the focal point. It always opens towards the focal point, or the focal point is always inside the parabola.